Okay, so my name's Nashir. I worked on this project alone, and it's titled Medical Image Synthesis for Data Augmentation and Anonymization via Diffusion. So there are a couple motivations for the research. One that we're very familiar with is that deep learning models take a large amount of data to perform well. And so I thought if you could augment the size of a training data set with synthetic imagery, it could improve the performance of downstream models. And that'd be really helpful in a medical setting, especially because there's also the patient privacy concern, and medical practices may not contribute their data to a large centralized data set. And so a potential solution is to generate some synthetic imagery and then pre-train on this and fine-tune on a small number of real patient images, maybe at each institution separately. And then that can be sufficient to develop a model that is performant enough to be useful while minimizing the use and sharing of real patient data. So there are three main components to my project. The first is to train the diffusion model. I train it to generate X-ray images with class labels, but if I had more time, I would like to try this on different data sets as well as maybe different downstream tasks. And then the second thing I do is I evaluate the quality of the imagery using metrics that measure the distance between distributions, real versus synthetic data. And then the downstream classification task that examines how the synthetic data affects the performance of classifiers. And as I said on the previous slide, the main goal is to help solve this data availability and patient privacy problem in MIC. So a little bit of review on diffusion models. I won't go too in depth, but essentially diffusion models are parameterized Markov chains that gradually denoise data. And this image on the right shows the denoising process for a model trained on the fashion MNIST dataset. So each time step, noise is iteratively removed from the image. And at the end, we see a shirt. So that's basically the synthesis process for diffusion models. And so diffusion models are trying to learn this denoising process. In this image, you can see that at xt, the image is pure noise. And at each step, p theta of xt minus 1 given xt removes a little bit of noise. So the diffusion model is learning this p theta. The problem with this for this application is that vanilla diffusion models don't give you images of a specific class. And I wanted to be able to have labels. So there's something called classifier-free guidance that uses training data labels during training to condition the diffusion. It guides it towards generating images of a specific class. And you can specify how much guidance you want using something called the conditioning score. And the image shows how different conditioning scores generate distributions with more separation between them. From left to right, the conditioning score is increasing. So in the literature, using a score of like 3 to 8 is good for generating images of a specific class. So I was lucky to find a good open source implementation of diffusion models by Lucid Rains, and I included the link in the slides. So I trained that on the Checkspert dataset that we're all familiar with from assignment 1. And I didn't use the full quality images due to computational constraints. It kept getting out of memory errors, so I reduced the resolution to 28 by 28. And I use UNet as the backbone for the diffusion model. And as far as sampling, I currently just use DDPM sampling, but I might shift to DDIM, which allows for synthesizing images in fewer time steps. Yeah. So to evaluate the quality of the generated images, the first thing I do is I use these distance metrics for say inception distance and kernel inception distance. And both of these are basically measures of how much the distribution of one set of images is different from the distribution of another set. FID was introduced in 2017 and KID in 2018, and they're both commonly used to evaluate generative models. And here you can see the setup for the downstream classification task. You can specify some synthetic labels with the class distribution that you want, use that to generate some labeled diffusion images with the trained diffusion model, and then can train a series of classifiers, one only on the real data, here I show only one on diffusion and real, but I would like to train on different percentages, maybe like 10, 20, 30, and so on, and see how the synthetic data, see the impact of it in data scarce versus data rich scenarios. And then one classifier that's trained only on diffusion imagery. And I want to quantify the difference between all of these. Yeah, so for the classification, I downscale the data to match what is output by the diffusion model. And here you can see all the hyperparameters that I use for training. As I mentioned on the previous slide, planning to train classifiers with different amounts of data. So first I've trained the classifier on the diffusion imagery, and then I fine tune it on some percentage of the real imagery. And I'm planning to evaluate the effect of that. And here you can see the loss plot for the diffusion training over 300 epochs. And it doesn't seem like the training is plateauing, so I plan to train this for more. And on the right, you can see the hyperparameters that I use for the training. And here are some results of the diffusion generated images I showed after 1 epoch, 45 epochs, 300 epochs, and then I also show the real imagery for comparison. So the quality of the images does seem to improve with more epochs. And as I said, the training didn't plateau, so I'm planning to train for more epochs. And another note is that when I trained initially, I used augmentations like rotation and random cropping, which is why the view of the chest seems to be a bit different. And so when I retrain the model, I'm planning to use non-augmented images and then apply augmentations to the synthetic data during training. Here are some baseline distance metrics. So what we're aiming for is something comparable to the real train versus the real test. Because those are going to be the most similar, we should expect an FID around that. When I train for 50 epochs, the real training data versus the real training data, the FID is relatively higher, but I bounded the FID that I'm expecting by comparing the real training data versus FMNIST, Fashion MNIST, because I figured they were relatively similar data sets, both grayscale, 28 by 28. And so I wanted to at least get something that is within that bound. So you can see that the FMNIST versus real train is about 223 FID. And the real train versus 300 epochs is 214. So I'm at least in that range. Hopefully I would like to improve these values. And I don't yet have the kernel inception distance implemented, which is why the table is not filled out there. And here you can see the results from the classifier training using all real data, 100% and 10% as my bound of what I'm trying to be in between. 100% is the best that I can get, and the 10% is a lower bound. And training on diffusion images is a work in progress. I generated some diffusion images, but not enough. But I have the training architecture set up to just plug and play once I have these images generated. So I plan to create plots like this showing the effect of all the different data splits. And here you can see that when there's less data used, as we expect, the performance decreases a lot. So another interesting idea about using the diffusion is that it can maybe be used to address the class imbalance problem without doing any class weighting on the original real data. So I plan to explore that as well. So work in progress, try to find ways to improve the generated image quality, experiment with different values of the conditioning scale. I'm currently using 3, which seems to produce good results, but I need to verify that when I actually train classifiers on that data. And then I need to train the classifiers. And I plan to implement some more metrics as well for computing image quality results. Yeah, so that's my presentation.